Okay, so let's go on to number 44. I'll recopy it here. This is a definite integral now. You notice it has limits of integration in it, so it will give us a number. It won't just be an algebraic expression. And this is integral x inverse sine x squared dx. Now you could try to just do integration by parts directly. You could say, for instance, u equals x, du equals dx. But then what would happen is you would have inverse sine x squared dx is left. So this must be dv, but how would you integrate it? So you'd run into trouble. How would you integrate that? It's not obvious how to integrate this. And so this is not a good method, so this fails. To try to do it directly like that. What's better is to do a substitution first. So what we're going to do is I'm going to say let w, now I'm using w here instead of u as a substituting variable, because later if I use integration by parts, I want to have a u and a dv, because that's what they're usually called in that formula. It doesn't matter what you call these things, it's just that this is a convenient choice. So w equals x squared, dw equals 2x dx. And if I wanted to, of course, I could write this as x dx equals 1/2 dw, because x dx is what actually appears inside the formula. And so then the integral is going to come down. This is going to be equal to the integral. Now there are limits of integration, and when I'm changing variables, it will change the limits of integration generally. So I have to think about that. But first I'm going to put in the variables, and then we'll worry about what the limits of integration do. So I have an x dx in here, and that's 1/2 dw. So I'm going to go ahead and take the liberty of putting the 1/2 outside. And there's going to be a dw here. And then what's inside is just inverse sine w. And now I have to worry about the limits of integration. Now, as x increases from 0 to 1, w also increases from 0 to 1. So it will turn out that the limits here are again 0 and 1, just like they were here. But see, that's a coincidence. That's not, you can't always just copy the limits from the last integral, because see, this limit meant limit from x goes to 0 to 1, whereas this one means w goes 0 to 1. And the fact that w goes from 0 to 1 as x goes from 0 to 1 is purely a coincidence in this context. I mean, if you graph x, it looks like this, if this is x, and then if I have, this is just x itself. And then if I have w, this is w equals x squared, if this is the x-axis. And it turns out that as I'm going from x equals 0 to 1, 0 to 1 here, that w also goes from 0 to 1. But it's a coincidence. So I want to make sure that you see that I'm not just copying the limits there. But all that's commentary, which we don't need now. Okay, so we have this limit here, or this integral now, and with these limits of integration. Now, it will turn out that a useful choice to make for the integration by parts formula will be to choose u to be this entire function here, inverse sine w, in which case du, do you remember how to differentiate inverse sine? It's du equals 1 over square root of 1 minus w squared dw. and then we're going to choose dv to be just whatever's left, which is only dw. And this seems like a strange choice to make, because you could think, well, how am I really changing anything? Well, watch what happens. So now v equals w. Now if I put this into the integration by parts formula, this will say this equals, I have my uv, so, well, there's a 1/2 out in front. So when I'm choosing the u and the v here, I'm ignoring the 1/2. I'm integrating this. I hope that won't bother you, the fact that now I'm putting the 1/2 in, because the 1/2 is out in front of this whole thing. So anyway, so what I get is a 1/2 here, and then I have the u. I'll tell you what, I could just put the 1/2 out in front of the whole thing like this, and then I could have uv, so this will be inverse sine w. V is just w. Now notice here I still have to evaluate this from w equals 0 to 1, because it's a number now. It's not just an algebraic expression. And then I have minus the integral of v du, which v is just w, du is this expression here, so this is going to give me w over the square root of 1 minus w squared dw. And so all that's inside there. Now what I accomplished by this is that now in this formula I can substitute in a new variable that is 1 minus w squared. Say I call that z. So what I'm saying here is in the second integral, I'm going to define a new variable, which I'm going to call z. So I'm going to say let z equals 1 minus w squared. Then dz is just minus 2w dw. And see, now I have this w dw that will match with the w dw here. And so it lets me do a substitution, whereas if I just had this here, then it wouldn't, I'd just get back the inverse sine. Okay, so now and these are still the same limits of integration for w here, going from 0 to 1. Okay, so I can either evaluate this first expression here and then do this one afterwards, or else I can carry this along until I simplify this integral, and I guess I'll do that. And maybe I have to erase some of this stuff up here because I'm running out of room. But so what I have now is I have 1/2. Open this. I'm going to simplify this a little bit, because I'm going to write w inverse sine w, just so I don't have to write the parentheses there. This is evaluated from 0 to 1. I took away the w equals 0 to 1. I don't know why I put the w there in the first place. I can, but it doesn't matter one way or the other. Okay, so then now here, this dz equals minus 2w dw. If I wanted to, I could have written this as w dw equals minus 1/2 dz, because the w dw is what I'm substituting in for. Okay, so then what will happen? Well, I'm substituting in a w dw for the dz, and so there's a minus 1/2 there, there's a minus sign here, so this will give me a plus. Now this is a 1/2 here, and then there's going to be an integral. And I have to worry about the limits of integration again, because I'm changing to the variable z. But then what do I have inside the integral? Inside the integral, I now have just I already took care of the 1/2, so what's left is just the dz, and then I have a 1 over the square root of this expression, which is z. So this is just 1 over square root of z dz. And now I have to worry about what the limits of integration are. Well, and I'll write that up here because I don't have anywhere else to write it. So as w increases from 0 to 1, which is what is happening, z is 1 minus w squared, so z decreases from 1 to 0. So what this is going to say is now the lower limit of integration here is 1, and the upper limit of integration is 0 when I'm working with c. So that's what I have here. I think I can write one more step down here. So this is equal to 1/2, and this is going to be, I guess I'll break this up into two pieces. I'm just going to write w sine inverse w from 0 to 1. And now I'm going to do the integral here. Now, I'm running out of room, so I hope you won't mind. Well, I guess I do want to do one more step here, because I want to change this to a minus integral from 0 to 1. Well, there's a 1/2 in front of it. And this 1/2 multiplies this 1/2, so that's going to go together to give me a minus 1/4 integral from 0 to 1. And then this thing I'm going to call z to the minus 1/2 dz. Okay, we're almost there. And what I think I'm going to do, I'm going to leave the integral here, and I'm going to take out part of this middle part. I don't need this part here either. So I'm going to take out this middle part. So I'm going from this now. So this is equal to 1/2 w sine inverse w, evaluated from 0 to 1. And then what I am going to have here is I'm going to have a minus 1/4. And then I'm going to have now z to the 1/2 divided by 1/2. That's the power law for integration. And this is evaluated from 0 to 1 for z. So this is going to give me 1/2. I'm going to simplify one more time, and then we'll substitute in values. Inverse sine w 0 to 1 minus. Now here I have a 1/4 in the numerator, a 1/2 in the denominator, so this will conspire to give me a 1/2 here, and then this will be z to the 1/2, or if I like, I could write square root of c, and that goes from 0 to 1. Okay, so now I'm going to have to scrub off this part. So I should now be able to substitute in values. Now I'm going to pull a 1/2 out here again. I probably should have left it there that way the first time, but I didn't. So let's put in, so I'm going to put in the 1 here. So this is 1 inverse sine 1 minus 0 inverse sine 0. That's this part here. And then I'm going to have a minus. And then I'm going to have a square root of 1 minus square root of 0. And then now I can just simplify that. So this will give me a 1/2. The 1 doesn't do anything. What's inverse sine of 1? The angle whose sine is 1. That's, well, if here's your angle, say I call it theta, as the angle is getting bigger, as it's getting closer and closer to pi over 2, then the opposite side is getting closer and closer to the hypotenuse, and sine is opposite over hypotenuse. So it's pi over 2 is the angle where the angle whose sine is 1. So this is just going to give me, inside here, I'm going to have just pi over 2, and then this 0 kills that. So all I'm left with from this whole thing here is pi over 2. And then this part, obviously, all I'm left with there is just 1. So the answer should be pi over 4 minus 1/2, because I distributed the 1/2 through here. And that's the answer. So that one took, the main issue with that one was just that it took a fair bit of writing stuff out. It required 2 substitutions. It required a little bit of a trick. I don't know, this is kind of maybe a substantial problem. It also involved worrying about what the limits of integration were. But if you can follow that problem all the way through, then you know a lot of useful things for doing integrals in general. Let's go on to the next one. So this is 56. And this is integral of 2x cubed cosine x squared dx. Now, the first thing I'm going to do is I'm going to make a substitution, and this is similar to what I did before. Because this looks complicated, I want to see if I can simplify it by letting w equal x squared. So let w equal x squared dw equals 2x dx. And then watch the way I'm going to write this. So I'm going to write this as equals integral of, I'm going to write an x squared cosine x squared. So I've taken out of this, I've taken it out of a 2x cubed, I've taken an x squared out, so I'm left with a 2x, and I'm going to put the 2x at the end here, 2x with the dx. Now why have I done that? Well, because that's exactly what shows up here, 2x dx. Now I can do the substitution. So I'm going to write this now as w cosine w dw. So that already looks nicer. Now I'm going to do my integration by parts. So I'm going to say let u equals w, du equals dw, dv is cosine w dw, v equals sine w. You might worry about the plus or minus here, but you can see when I differentiate this sine, I'll get a positive cosine, so that's why it's the right choice. So then the integral becomes, I have my uv, so this is w sine w, minus the integral of v du, so this is sine w, du is just dw, dw here. And so then this becomes integral w sine w. Now when I differentiate a sine, I get a positive cosine. So when I integrate a sine, I ought to get a negative cosine. So I have to get minus cosine w plus c. And now I can substitute in what the w is. So this is x squared sine x squared minus cosine x squared plus c. And that's not so bad. That's much more convenient than what the last one was. Okay, so we have one more in this section. And that's a proof, and it's actually a very easy proof. It's an immediate proof. It comes in the integration by parts formula. So we want to prove this formula that if I integrate some power of x times a cosine, that I get an expression where I have x to that same power times sine minus an integral, which is n times an integral of one lower power times the cosine. So if I begin by writing out the integral on the left-hand side, so this is x to the n cosine x dx, and I let u equals x to the n, then du will be n x to the n minus 1. dv has to be cosine x dx. in which case v is just sine x. Once again, if you worry about the plus or minus, think about differentiating this and you'll get a positive cosine, so that's why it's correct in this case. So what do I get? Well, this integral here then just becomes, this is equal to, it's awkward to write a vertical equals like that. So let me just write this. I'm going to write the integration by parts formula. Integral of u dv equals uv minus integral of v du. What does this become with these particular choices? Well, the u, of course, was, this is just the left-hand side here, x to the n. The dv was cosine x dx. This is equal to uv, this is x to the n, v is sine x, minus the integral of v du. What was v? This was sine x. du is just, I forgot my dx here, sorry. n x to the n minus 1 dx. And the only remaining step is just to pull out the n in front here. So this is x to the n sine x minus n times the integral of, and also to interchange the order of the sine x and the x to the n minus 1 part. So this is x to the n minus 1 sine x dx. And that, when I take this here, is precisely the formula that I wanted to show there. So this was some problems from section 8.2 involving integration by parts, and you saw how we also had to use substitutions as well. So that kind of puts together two things, and hopefully that, well, it shows you some interesting integrals and ones that if you know how to do those, you'll know how to do a lot of others as well.